What I want to do in this video is think about the different ways to represent a molecule. So the most obvious way is its name. So for example, you could be referring to a molecule of benzene. Benzene. But just the word benzene tells you very little about what actually makes up this molecule. And there's other naming conventions that do give more information, but you might say, well, I actually want to know more about the actual particular elements that make it up. Well, that might be, in that case, it might be useful to move up to the empirical formula. Empirical formula. And you might be thinking, what does empirical mean? Well, in general, the word empirical is referring to something that comes from observation or comes through experiments. If you could say, hey, from empirical evidence, I now believe this. This means that you saw data. This means that you have some observations that make you think this new thing. And the reason why we call what I'm about to write down an empirical formula is because early chemists would have been able, they weren't able to look at just one molecule, but they could at least come up with, they could observe the ratios that it seemed like of the different elements that they had in a molecule. So an empirical formula gives you a ratio of the elements in the molecule. So an empirical formula for benzene is, it is 1 carbon for every hydrogen. Now you might say, okay, that's nice. I now know that if I'm dealing with benzene, I have 1 carbon for every hydrogen or 1 hydrogen for every carbon. But how many of each of these do you actually have in a benzene molecule? And to answer that question, that's when you would want to go to the molecular formula. Molecular formula. And the molecular formula for benzene, which is now going to give us more information than the empirical formula, tells us that each benzene molecule has 6 hydrogens and, 6 carbons and 6, I'm really having trouble today, 6 hydrogens, 6 carbons and 6 hydrogens. Now the ratio is still 1 to 1. You get that right over here. It's very easy to go from a molecular formula to an empirical formula. You essentially are losing information. You're just saying the ratio. Okay, look, it's a ratio of 6 to 6, which is the same thing as 1 to 1. If we wanted to, we could write this as C1H1, just like that, to show us that the ratio for every carbon we have a hydrogen. And we see that that's actually the case in one molecule. For every 6 carbons, you have 6 hydrogens, which is still a 1 to 1 ratio. But that might not satisfy you. You might say, well, okay, but how are these 6 carbons and 6 hydrogens actually structured? I want more information. And for that, you would want to go to a structural formula. Structural formula, which will actually give you the structure, or start to give you the structure of a benzene molecule. A benzene molecule would be drawn like, so you would have 6 carbons in a hexagon. So 1, let me write it this way, 1, 2, 3, 4, 5, 6 carbons in a hexagon, just like that. And then you have a double bond. Every other of these bonds on the hexagon is a double bond. And then each of these carbons are also attached to a hydrogen, also bonded to a hydrogen. And each of these lines that I'm drawing, this is a bond. It's a covalent bond. We go into much more depth in other videos on that, but it's a sharing of electrons. And that's what keeps these carbons near each other, and what keeps the hydrogens kind of tied to each other, or the hydrogens tied to the carbons and the carbons tied to the hydrogens. So let me draw it just like this. And this is only one variant of a structural, it's hard to see this, that one I just drew. So let me see if I can do a little bit. That's about as good. Hopefully you see there's a hydrogen there, and there's a hydrogen right over there. And this is one variant of a structural formulas. Some structural formulas will actually give you some 3D information, will tell you whether a molecule is kind of popping in or out of the page. Others might not be as explicit. Once you go into organic chemistry, chains of carbons are just done, you might see something like this for benzene, where the carbons are implicit as the vertex of each of there's an implicit carbon at each of these vertices, and then you say, okay, carbon's got to have is typically not gotta, but it's typically going to have 4 bonds in its stable state. Well, I only see 1, 2, 3. Well, if it's not drawn, then it must be a hydrogen, and that's actually the convention that people use in organic chemistry. So there's multiple ways to do a structural formula, but this is a very typical one right over here. So as you see, I'm just getting more and more and more information as I go from empirical to molecular to structural formula. Now, I want to make clear that empirical formulas and molecular formulas aren't always different if the ratios are actually also show the actual number of each of those elements that you have in the molecule. And a good example of that would be water. So let me do water. So let me do this in a different color I'm pretty much used every color. So water. So water, we all know, for every 2 hydrogens, and since I already decided to use blue for hydrogen, let me use blue again for hydrogen. For every 2 hydrogens, you have an oxygen. You have a oxygen. Now, it just so happens to be that what I just wrote down, I kind of thought in terms of empirical formula, in terms of ratios, but that's actually the case. A molecule of a molecule of water has exactly 2 hydrogens and 1 oxygen. And if you want to see its structural formula, and you're probably familiar with it, or you might be familiar with it, each of those oxygens in a water molecule are bonded to 2 hydrogens. So hopefully this at least begins to appreciate different ways of referring to or representing a molecule.